All right. I think we're live. So let me present Amartya, who once again talked about extended reflection positivity for topological quantum field theories. Please, Amartya, take it away.
By the way, it's going to be recorded, right? Is the recording on?
Yes, it is.
Right. Cool. So yeah, thanks again. So okay. Right. So as is the part 2. So a quick, very rough plans, the stuff that I'll be talking about. So in the first talk, if you can follow the first talk. The first talk was like they basically talked about a bit of the physics motivations, and then introduced the notion of topological quantum field theory, and then also defined. Okay. So before that, let's go through a very rough plan for what is in store for today. So today, so in the previous talk, if you have attended the previous talk. So previous talk, I talked about discrete, invertible topological field theories. So today I'll introduce continuous invertible topological field theories. Then I'll talk about, then I'll introduce reflection structures on my folks. And then the way we are defined in invertible topological field theory will incorporate the notion of a reflection structure in our definition. Then I'll briefly talk about stability, and then a few final remarks, and a few words about the third part. That is the next part. So let me begin by writing down what we had ended with in the previous talk, in the previous part. So this is the result that we kind of had. Okay. Let me make sure. Okay, yeah, this should do. No, I like this one, so I'll use this. Oops. Cool. So the last result, something that we last theorem of the previous talk, deformation classes of discrete, invertible, n-dimensional, extended topological field theories with symmetry. So basically identifying the homotopy type. Right. So now, okay. So first, I won't talk as in again. I won't talk as in won't get into the details of the physical notation. So I'll just introduce what I mean by a continuous invertible and dimensional extended topological field theory. So a definition. So continuous invertible and dimensional extended topological field theories. Okay. Although I'm already in, but okay, maybe a few words that I should have said before. So yeah, this will mainly be us understanding about reflection structures actually. So the most part would be understanding reflection structures, and then in the next talk I will talk about positivity and extended topological field theories, and then talk about our main theorem. Right. So this is mostly about understanding what reflection structures are. Right. So this is just right. Okay, so back to our definition. So continuous invertible and dimensional extended topological field theory. That's symmetry. which is a spectral map. We talked about maximum Tillman spectrum in the previous talk. We've also talked about the Anderson dual and character dual in the previous talks. So, okay, so as in the other cases, so again, the spaces of the subspaces of these, the space of these theories would be so this would be right. So this is our definition. So we'll see more actually towards the end. Okay, maybe not towards the end, maybe yeah. In the next talk, we'll do some obstruction theory with continuous extended n-dimensional topological field theories with symmetric group HN with reflection structures. We'll do some obstruction theory in the next talk. So I'll kind of explain a bit about why we are interested to do that towards the end of this talk. So okay. So we'll begin by talking about, okay, so now comes the main part, which is mostly, which will occupy most part of the talk. So this is about reflection structures. Right. So first remark. So we had seen that we have a map. Right, we had defined this map. Right. So now, so first an observation that is HN, the symmetric group HN. It fits into a sequence of compact Lie groups. It's a sequence of compact Lie groups. So this K is basically the kernel of this map. Right. So this is an observation that we have, and we'll use this to. So this will come in hand actually in defining HN structures on that course. Right. So now we'll talk about manifolds and Boardism categories with HN structure. So that is what we'll be talking about now. So okay, so I'll start with defining what I mean by a HN structure. So an HN structure is a pair consisting of a principal HN bundle equipped with an isomorphism of principal and bundles. So I'll define all which they have. So I can recall this rho n is the map that we have over here. Okay. So maybe I'll try and wherever. Okay. So yes, this is the principal and bundle of frames. Just recall. So when I say that, that means that the point BOX is, so that would just be the orthonormal basis of the tangent space of X. Right? Then for our principal HN bundle, say again B to X. Right. With so basically have for all Right, so just to recall. Okay, now I'll define differential, also what are differential Hn structures. So now we have notion of an Hn structure. Now got the differential. Hn structure is a connection. So we need lambda such that theta maps, so theta we define theta maps the connection to lambda. Oops. Okay, so just to recall the Lewis-Theta connection. So there is an affine connection that preserves, so that that preserves the metric and distortion free. Right? So just to recall to this one. Right. Okay. So now, so maybe another definition. So an Hn manifold. So by this I mean a manifold, which is more short form, is a Riemannian and manifold equipped with an Hn structure. So okay, maybe a remark. I'll add this. So for n-1 dimensional manifold, an Hn structure. Just set this one. An Hn structure can be given by, I may have said this, but by stabilizing the tension by summing with the trivial, dimensional boundary. Well, by summing with the trivial line boundary. So I don't know, whatever. So another remark. This is an important one. So morphism. So how do you look at morphisms in the Bordism calculus? So morphism, say from any calculus in scaling. So there is a compact and manifold Hn structure and isomorphism boundaries. No, the thing is that, so when we are, okay, so now here comes, so I had promised in the first talk that I'll explain why we call this extended reflection positivity. So here's where the extended comes from. So for talking about extended positivity, we need to pass on to the extended symmetric group. Right? Extended, which is, and this is where the extended symmetric comes into the picture. So now, so suppose we have an inclusion. So let me call this J. So okay, let me see this. So we can extend a principal Hn bundle to a principal Hn times this. So this one, okay, let me write this. We can extend say B2. That should so this is the J that you, and similarly we can like theta also extends to an isomorphism. Theta extends iso children. Oh, sorry. Oh, okay. Let me just call it theta hat. Over principle. Right. So now for reflection positivity, we'll talk about the notion of an opposite H in structure. So definition, quick definition. So the opposite H in structure. So that is just H and R. So this is what I call. So now structure. It's a principle H and bump. And the restriction. So theta dash is a restriction of theta hat. Right. So, okay, so let me give an example actually. It's a very straightforward example that you can think about, just which is also easy to picture. So, you know, what drawing we'll just write it down. So in structure, it's just an orientation, right? So this is the best example that you can think about. I mean, the most easy that I can think of. Then the opposite. So this is just a reversible. Right. Okay. So now. So okay. So now okay, let me see. So I'll have to. There are a few things that I have to define before I talk about reflection structure. So let me see. Okay. So first I'll define what I mean. What I mean when just let me think about this for a second. Okay, maybe I can do that later. So let me go along. Right, so I am okay. Okay, I'll do that when I need to. That's okay. So now, so let's define a few so involutions that will play a role when we talk about reflection structures. So let's define the involution which theta sub b so that just fixes the underlying manifold. Underlying manifold and then involutes. Right, so that is this inclusion. This will play a role. We'll see in defining reflection structure. So now an important that of course I want to so for we have a canonical isomorphism. Oh, oops. This is just the doer. So this just means, so by this, so this means that you, so another way of saying this is that every object, okay, every object in this course has a Hermitian structure. Let's think it as a definition for now. So similarly, let's define complex configuration also. So again, we define this is C. So this is complex conjugation. Now, so after we define these, so now we are in a position to define reflection structure. Then I'll explain, so we'll kind of unwrap the definition. So reflection structure on a topological field theory, so say F is the equivariance data. So I'll explain what I mean by data. That means data B and data C. So I'll define what I mean by equivariant data. But before that, so let me talk about, so for that, so for the setup, so we need something. So let me define that first. So what do you mean by an involution in a category? So an involution in a category C is a function that corresponds to an object, so corresponding to an object, so say X of C is equal to action. Right, so this determines morphisms, the morphisms and the morphism of C. So in sigma, the sigma would be important. So please make sure that just pay a bit of attention to the notation. There's a lot of notational stuff. So it says that this is the notion of an involution. So then again, okay, so there exists, so you can reformulate it in a different way. So I can just say that we have a natural isomorphism. So yeah, natural isomorphism. So for our purposes, okay, maybe I don't need to, but okay, let me call this data. About natural isomorphism. So now, so okay, what do I mean by equivariance data? So now I can. So first we have two categories, X and X dash. Okay, so maybe I should say C and C dash. X for the objects. C and C dash are categories with involution. So I just define what is the thing. We have a functor. So then equivariance data for is an ISO. So remember the sigma that we defined. Okay, let me just put this slide. So yeah, this is sigma that we defined, right? This is sigma C. It's for the category C. Okay. So it is an isomorphism of the small functors from C dash, such that for all X in C, the following commutes. So we have a track for the following commutes. So again, so define what I mean by, so this is the natural isomorphism, that I just defined. Yep. Yeah. So this commutes. Right. So this is what I mean by, so that is the basic idea. I say a reflection structure. Right. So now, right. So now I think, so for every closed and minus manifold Z with the Hn structure, we have an isomorphism of X spaces. Right. So now, so combining this, this previous, so combining, okay. So we had stated important propositions where we just go back. So we can maybe call it star, or maybe something, just square. So proposition square. So we use proposition square to get something. So using proposition square and whatever we saw just right now. So this is what we'll get. I'll just call it H set. This would be nice. Which right, this is something that we do. Cool. So now I can talk about what it means for a reflection structure to be positive. So I will talk about positivity in detail for extended topological field theories the next step. But what does it mean for a reflection structure to be positive? So that's where we are right now. So definition. A reflection structure is positive if the induced Hermitian. So this was a Hermitian form that we got. Right? So this, right. So the induced Hermitian, say H said, is positive, definite for all boards. All right. So now we are one step closer to incorporating the notion of reflection. So reflection structures in our definition of invertible field theories. So before that, we have to talk about the extended switch, right? So again, this part would be a bit sketchy. I won't. There'll be an important proposition that we'll be using for our definitions. So this part, yeah. So I'm saying everything in detail. So for so because of the physics part, actually, so for that I have to talk about HN structures, Euclidean quantum field theories and things, and which I think is easy to understand from a different perspective, at least to me. Okay, so maybe you can black box it. So this is right. So the extended symmetrical. So HN is viewed as a symmetrical of Euclidean quantum field theory, which I have not defined. So you just think, okay, so maybe you just think about this to be you're just adjoining involutions to HM. Just think about it like that. That'd be good enough for us so far. So okay, I won't get into details. So proposition, so this is proposition 3.13 in the Freed-Hopkins paper. So there exists a canonical group extension. So I'll call this J. So this group extension will be very important for us, and we'll see how. So how we'll use this to define. To define our. So we'll see. So first, let me go through this first. So I'll write the proposition to it. So there exists a canonical group extension that is split by a choice of hyperplane reflections, and choice of hyperplane reflection that are such that the splitting automorphism. Right. That is the project, that is the product of conjugation by the side and identity automorphism. Yeah. So okay, I didn't say what K is. I'm sorry. So K is the internal symmetry. So continuing, there exists a homomorphism such that we have in the following pullback diagram. Oops. And there exists solutions for right. Okay, so this will help us. So this is the central pair actually. This will extension of the law. So this will okay, so let me write this down. So the previous group extension. So I'll call this whatever. I hope I'm not use stars anymore. So it induces Z mod 2 action BHM and makes the vector boundary into the equivariant vector. So we'll have a, so we get a Z mod 2 equivariant from spectrum. So that will denote as follows. So now, yeah, now we are in a position to define this. Okay, so okay. So maybe before that, before our definition, maybe I should define the real structures. But I think structures. Okay. So let me do that. Real structures. Or maybe okay. Maybe let's see the definition first and we'll try and unpack it. Cool. Real structures. Let's see real structures. So first, starting with the discrete version. A discrete, invertible, n-dimensional, extended topological field theory with function and reflection structure. So that's just an equivariant. So H. What does that have to do? So yeah, so I'll talk. Let's see what this means, and I'll talk about when I talk about real structures. When I have the unpack the definition. Then a continuous, invertible, and dimensional extended. And collection of this equivariant line. 5. So I'll talk about all this. Okay, so the space of these theories I have because it's just simplification. So I'll just add that. See how useful this will be in the next one. Right. So now, okay, so now let me talk about real structures. So again, so this is like, so first, sorry, yeah, so this is like unpacking. For unpacking a definition, we are defining something else, which also will have to unpack. So let's check the definition first. So the space of real structures, that's the space friction is the path component. Of the space. So I define the space. This is why now, but I can find it more. This is like unpack. This is containing. So first the definition. So it's the sigma, so this is just the real sign representation. So I'll denote this by gamma, right? This man. Okay, so what is this? So for that, so for the things. So first let me write this up. Complex conjugation. Is corresponds to a map. So, here. Oh, okay. Okay. So this is basically some hormone of several homotopy equivalents. Isn't that simple? Right. So complex conjugation and that's so this is the map with a property. Property with at least the property rather. Because there are other things in the picture as well, that it's effect on I1 is the sign representation. Now, so this would be is the space of maps, including this homomorphism that I had, as I said. Right. Then so this would be union of many path components of this problem. Right. So that was unpacking unpacking the definition. So okay, it's another definition. So now real structures in the character duo. The space of the real structures. So we saw this what the space of real structures. Anderson duo was space of real structures. How's it all right? And we'll define the space of real structures in the character duo in terms of that. Oops. Here's the path component. Corresponding to the space of real structures. Under the following equivalent, so we have this equivalent, so they have not stated this here in its time. Yeah. Right. So, oh, So then, that's almost there. So this would be, so this is something that we saw in the previous definition. So this set mode to spectrum corresponding to a real structure. So we had this equivalence that are those double stuff. So under the equivalence double star that we define to be as sigma. So sigma is the real chain representation. Induces a real structure. So after this, so let's revisit the definition again. So just knowing about so they make no sense. Oh, so yeah, so discrete, so as you can see, so here's this zero dash, and this gamma. We had defined these form spectral before, so okay. So maybe this wasn't the most efficient, the most pedagogical way to introduce this, but yeah. So now, okay. So before ending this again, so now I define what I mean by stability. Right? Information stability, maybe just a definition, but I'll just talk a bit about what's upcoming for the next talk. So an n-dimensional invertible topological field with the domain to be was stable if it's the restriction of some theory defined. So that is the notion of stability that we have for this. So there's the notion of stability for an inhibition and vertical topological field theory. Let me see. Things that we'll see in the next talk a bit. Yeah, so let's again, let me give it a thought for a second. Okay, so yeah. Right, so the next talk I'll talk about stability for discrete. So two things we'll see. So we'll see stability for discrete invertible topological field theories without reflection structure, and continuous invertible topological field theories with reflection structure. We'll also see why those are the ones that they're interested in. Then so then we'll use construction theory to before that I'll also talk about positivity for extended topological field theories, and Yeah, then I will use obstruction theory for a kind of the characterization of stable, discrete, and continuous theories. Right. So we'll do obstruction theory with the sequences of matching Tillman spectrum. Then then I'll prove the main theorem. So the main theorem basically is like so that gives us an identification of the homotopy type of the space of invertible, continuous, reflection positive quality topological. So that is, I can write this down. So the main goal at the end of the day. So identification. So maybe I had not said, I had not mentioned this in the first talk. So identification. So this is the main goal of the homotopy type of the space of invertible continuous reflection positive. So I'll talk about what I mean. I'll define what I mean by reflection positive. Extended topological confinement theory. Reflection positive. Yeah. So this is the main goal of this kind of series, whatever. So yeah, well, with that, yeah, I'd like to start.